In this video we shall study a few more power amplifiers. Can you remember this waveform? So this waveform is nothing but the output waveform of a class B push-pull amplifier. So you can see here, so whenever the input voltage or the output voltage crosses 0, so there's a distortion. So this distortion is called as a crossover distortion, which is due to the non-biasing of the transistors. So since the transistors are not biased, the conduction angle is slightly less than 180 degrees. So we end up with distortions. Even though the class B push-pull amplifier has got very good efficiency, it has got this crossover distortions. So in this class AB power amplifier, we have to overcome this crossover distortions. So in order to overcome this crossover distortions, you can see the circuit diagram, which is identical to that of a class B push-pull amplifiers. Just see the difference between the class B push-pull amplifier and class AB amplifier is, so we have two DC voltage sources, VGG1 and VGG2, which is used to bias this M1 and M2. So the VGG1 and VGG2 are such that, so even if the input voltage is negative, this M1 is conducting. That is, this is going to conduct for an angle greater than 180 degrees, meaning so it will be conducting even beyond the positive half cycle. So the VGG2 amplitude is such that even if the input amplitude is positive, this M2 will be still conducting, meaning this class B power amplifier will going to have two transistors which will be conducting for more than 180 degrees. So since they are conducting for more than 180 degrees, the overall conduction angle happens to be 360 degrees. Whatever crossover distortion we had it in the case of class B push-pull amplifiers will be overcome. So we're going to have a gain of 1, and you can see there is no distortion coming here. So the class AB power amplifier is one which is identical to that of class B push-pull amplifier. So only thing is that here we have two DC voltage sources which will make the M1 and M2 conducting for more than 180 degrees. The efficiency of this class AB power amplifier is identical to that of class B push-pull amplifiers, around 78%. Now we shall have a look at this LC circuit. So assume that this capacitor C and L are ideal capacitors and inductors. If I open the switch and if there is a voltage stored in this capacitor, that is initial voltage we initially stored over here. By the moment I close the switch, now this whatever charges that have been stored will be dissipated onto this, and this will going to further deliver the charge into this. So it will be keep on exchanging between the inductor and the capacitor and the inductor, and from inductor to capacitor. So we end up with an oscillations coming. So this will be a sustained oscillation as long as these two are ideal in nature. So we'll end up with a sinusoidal oscillation at a frequency f, which is given by 1 over 2 pi root LC. So this value of L and C will decide the oscillating frequency. So as you can see now, when switch is open, so the V0 is the DC voltage. When switch is closed, its oscillations, we end up with sinusoidal oscillation at a frequency equal decided by the values of L and C. But what happens practically, because these two are not ideal diodes, they're going to dissipate the power in them. So practically we'll end up with oscillations dying out as time elapses. Now if you close the switch, for some time it will oscillate, and finally it becomes the oscillations will die out. Now you should see this circuit. Now you can see we have the similar circuit, but now the switch is closed permanently. We have a current pulses being induced into this. You can see since the current pulses are induced at this fashion, meaning for every positive half cycle I am giving a pulse here. So there is one more positive half cycle, I am giving a pulse. So there is a pulse, there is a pulse. For every positive half cycle I am giving a pulse. So F pulse, the frequency of this current pulses is equal to the frequency of the oscillations. Now since even though this L and C are practical in nature, the oscillation is not dying out because we are giving the required energy which is being lost during the power dissipation through these current pulses. Now as long as these current pulses are there giving the energy that is being lost due to dissipation, we're going to have a sustained oscillation. It is not necessary that the pulses should have a frequency equal to f. Even if I give the pulses by skipping one signal, so we're going to still get the oscillations, meaning if the input pulse frequency, the current pulse frequency is equal to this f, we'll get the oscillation. Even if it is half of that, we're going to get the oscillations, meaning that for harmonics of the frequency f, we'll be still getting the oscillations here. So this V0 will be a sustained oscillation as long as we get the current pulses at frequency f, 1 by half of f, 1/3 of f, 1/4 of f. Suppose if this frequency is low and low, so there is a possibility that this may die out before the next current pulse comes. So that's why it's usually the current pulses are given every positive half cycle so that we get a sustained oscillation. Now this is the basic for another type of power amplifiers, which is named as class C power amplifiers. As you can see now, so this MOSFET is not biased by any external resistances. Whenever the input voltage is above threshold voltage, now you're going to get a current. So since the load is nothing but a LC component, so this ID acts like a current pulse for this. So as we discussed in the previous slide, so this is the current pulse which is being produced during the positive half cycle of the input voltage. So these current pulses will keep these oscillations existing with a frequency equal to given by 1 over 2 pi root LC. So this L and C will decide what is the oscillating frequency of this. Now this is again the op-amp will be conducting for very small duration of the half cycle. Of course, it may not be conducting for the entire cycle. Again, this is an ideal case. So if it is less than VTH, it won't conduct. So you want to have current pulses like this. So you want to have a small current pulse. Again, it is 0 with the small current pulse, which is enough to keep this oscillation sustained. Now we shall see, okay, how do we find the power conversion efficiency? We know that efficiency is PAC by PDC. PDC is nothing but the power that is being dissipated in the transistor due to power that is being drawn from the power supply. So that is PDC here. So let's just have a look at what is PDC now. So this is VDD. How much is the amount of power that is being drawn from the power supply? Since I is the current flowing through the entire circuit, the PDC is given by VDD into ID. So what is the power dissipated in the MOSFET? We know that we just name it as power dissipated in the MOSFET is nothing but PT. So we know that when the MOSFET is conducting, then only it dissipates the power. Whenever it is off, the power dissipation in the MOSFET is 0. So when the MOSFET is on, so usually the VDS voltage is very small, so it is VDS sat. So we shall just take the power dissipated in the MOSFET whenever it is on is the current flowing through this multiplied by the voltage across this MOSFET. Voltage across the MOSFET when it is on is VDS sat. So that's what is here. So PT, the power dissipated in the MOSFET, is given by VDS sat into ID. Now we know that out of the entire power that is being consumed from the power supply, which is PDC, some of the power is being dissipated in this LC component, and some of them is dissipated in this transistor, the MOSFET. Now PDC should be equal to the AC power that is being dissipated in this LC and the power dissipated in the transistor. So naturally we don't know exactly what is the power dissipated here. Since we know what is PDC and what is the power that is being dissipated in the transistor, so the PDC is actually the PT, that is the power dissipated in the MOSFET, plus the power dissipated in the LC tank circuit. So from which we can find what is PAC, which is only about PDC minus the power dissipated in the transistor. So which comes out to be VDD minus VDS sat into ID. So this is the actual AC power. So since you know what is PDC and PAC, we can certainly estimate what is the efficiency here. So upon substituting this PAC as per this equation, let me take out this VDD outside. It will be 1 minus VDS sat by VDD into ID. So that's what is written here. And the PDC, the power dissipated from the power supply, is VDD into ID. So upon solving this, okay, VDD will go with ID will go off. we'll end up with 1 minus VDS sat by VDD. So as we know that VDS sat is very small compared to VDD, so this is almost the efficiency is close to 1, or the efficiency of this class C power amplifiers is above 90%. This way, these class A power amplifiers are the best in the class, which are going to give a power conversion efficiency of more than 90%. So we have seen a different type of power amplifiers starting from class A transformer coupled. We have seen class B push pull amplifier. We have seen class AB, and then we have seen class C also. In the next slide, let us summarize all the power amplifiers. So this is the type of the power amplifier class A. You can see the circuit diagram. You can clearly notice that class B is one where there is a biasing provided, so that this conducts for entire 360 degrees. So this is a circuit diagram. These two transistors are used to provide the required current. This is the active transistor, so V0 is almost close to Vin. The swing of the output voltage from VDD to minus VSS, we're going to have twice the VDD as the swing. The conduction angle is 360 degrees. The PAC, so since you know the output waveform, we can find what is PAC. The PDC is twice VDD into I, because why it is twice means it is VDD over here and minus S over here. The difference happens to be 2 times VDD, assuming VSS is equal to VDD. So the efficiency happens to be hardly 25%. This is a theoretical one. Practically it will be less than 20 to 10%. In class B push pull amplifier, so here the circuit is not at all biased. So we have two MOSFETs. So this will be conducting during the positive half cycle. This is during the negative half cycle. We end up with a waveform which is having a crossover distortion. Now each is conducting for 180 degree and 180 degree. So overall it is 360 degree. It is slightly less than 180. And we're going to have the PAC in this case also identical to that, because it's again a pure waveform, a sine waveform barring this distortion. The PDC changes here because each of the MOSFET is conducting for only half cycle. That's why we wrote IDC is nothing but IM by 5. So that's because of that we have the PDC is given by this expression. Upon simplifying, we got the efficiency as 78.5%, which is one of the best power amplifiers, which is giving a very high efficiency. So we have seen class A amplifier has got a very poor efficiency. We have also considered a transformer coupled class A power amplifiers. So the advantage of having this transformer coupled is this RL, which is small, will look like a very high impedance here. One more advantage is that the output swing is twice the VDD because of the counter EMF that is there in the transformer. So we got the expression for PAC as VRMS into IRMS, so which is given by VDD into I by 2. So we have the PDC, we have only one current, one voltage source which is being used as a supply. You can see this is also biased with R1 R2, so that it conducts for the entire 360 degrees. So we have this as only VDD into ID. So here it is 2 VDD into ID because we had 2 power supplies. Now it is only one power supply, that's why it is VDD into I. So the efficiency is actually increased by 50%. Now it is efficiency 50%. We also saw in the previous slide the class C power amplifier. So class C power amplifier has got a tank circuit, which is LC tuned circuit, having the value of L and C, which decides the oscillating frequency of this. And this is also not biased. This MOSFET will be conducting for a very small period, which is less than 180 degree. Now, since it is LC, the output waveform is a pure sine wave. So we'll get the output voltage. Now, in order to find out the efficiency, we cannot find what is PAC directly, but we can certainly find what is PDC here, which is nothing but VDD into I. We can estimate what is the power being dissipated in this MOSFET, which is PT, that is VDS sat into I. So once we know what is PDC, the entire power drawn from the power supply will be dissipated in this output power and the transistor power. So that's why we can estimate PAC by subtracting PDC minus PT is going to give PAC. So this is what the expression. Upon finding, it was found that the efficiency is more than 90%. So this way, this is the summary of efficiency of